Okay, let's unpack this. Have you ever really stopped to think about the surprisingly complex engineering that goes into creating just the right environment for living things indoors? And I don't mean us.
Right.
We're talking about places meticulously designed for everything from, commercial livestock to tiny lab animals, even research-grade plants.
Yeah, it's a whole hidden world of engineering.
So today, we're doing a deep dive into the technical blueprints behind these controlled worlds,
Oh.
our source material. It takes us straight into the detailed world described in a chapter of the ASHRAE Handbook, specifically focusing on environmental control for animals and plants.
And right off the bat, this handbook, it really lays out the fundamental challenge engineers are grappling with here. How do you balance the very real biological needs and the productivity potential of these organisms
Right.
with the significant costs involved in modifying their environment so precisely? It's not just about keeping them comfortable. It's engineering for life, yes, but also for, well, the economics of production or research.
So our mission today is kind of to cut through the technical jargon, pull out the most important nuggets, look at some fascinating real-world examples, maybe some calculations,
Yeah, definitely.
and really understand what goes into tuning these indoor climates for, peak performance. This is your shortcut to getting well-informed on a critical, if maybe a bit niche, area of engineering.
Absolutely. Where should we start? Animals.
Let's start with animal environments. So, at a high level, the goal for animal housing seems straightforward.
Mm.
Keep the thermal and air quality conditions within a healthy, productive range. But the real driving force behind the design.
Well, it's the bottom line, often. The equipment costs, the energy costs they have to pay for themselves somehow, through increased production, better animal health, or maybe more reliable research outcomes. It has to make economic sense.
Exactly.
And the standard design approach, it usually involves using steady-state energy and mass conservation equations. Think of it like balancing the books for heat and moisture. Now, sometimes you need more complex transient analysis for tricky situations, but the handbook really emphasizes that getting the fresh air exchange rate right, figuring out how much outside air to bring in, and then distributing that air properly, those are usually the absolute most critical design decisions.
And there's a whole logic to how engineers figure out that ventilation rate, isn't there?
Yeah.
I saw a kind of curve based on outside temperature that dictates the strategy.
That's exactly right. It's a logic curve. So in cold weather, you might think ventilation is mostly about temperature, but it's primarily driven by moisture control.
Moisture, really.
Yeah, keeping humidity below a certain point, usually 70 or 80% RH, to stop condensation forming on surfaces. And also, keeping contaminants low for air quality. This nearly always means you need supplemental heating to maintain the target temperature while you're bringing in that cold, drier air.
Okay, so cold weather, moisture and air quality first, heat second. What about when it warms up?
As the weather gets milder, the amount of ventilation you need just to keep the temperature from rising too much, that actually becomes more than what you strictly needed for moisture or basic air quality control. So you're increasing airflow mainly to temper the indoor climate.
Got it. And then hot weather.
Hot weather, it's all about minimizing that temperature rise inside and, critically, providing air movement over the animals to help them shed body heat. Cooling systems might kick in, like evaporative cooling, but the handbook does note there's a practical upper limit to just cranking up the fans, often around 60 air changes per hour. Beyond that, it gets inefficient or impractical.
60 air changes an hour? That's a lot of air moving. So how do they calculate the actual heating or cooling needed? You mentioned heat balance.
Yeah, it's called a sensible heat balance. Basically, accounting for all the dry heat, you add up the gains, body heat from the animals, heat from lights, equipment, maybe warm air coming in, and subtract the losses, like heat going out through walls or roof, or lost when you ventilate with cold air.
Okay, like balancing a checkbook for heat.
Exactly. You need good data, like how much heat different animals produce. The ASHRE Handbook Fundamentals volume has tables for that. Then you pick your target indoor temperature based on the species.
Which the handbook provides examples for too, right?
It does. And you use the outdoor design temperature for your climate. The difference tells you how much heating, cooling, or ventilation you need.
And moisture control is just as critical, you said. Where does all the moisture come from? Just breathing?
Breathing and skin evaporation, yes, that's latent heat production. But also, quite significantly, from spilled water drinkers, cleaning and evaporation from manure and wet floors.
Manure.
Right. And here's a really interesting practical example the handbook points out. If you design, say, a swine facility with a totally slatted floor, so the manure drops through,
Okay.
That single design choice can cut the amount of water vapor you need to remove via ventilation by up to 40% compared to a solid concrete floor where moisture pools and evaporates.
40%,
Yeah.
just from the floor type. That's huge. That must have a massive impact on heating costs in winter.
Absolutely. It reduces the minimum ventilation rate needed. So the overall humidity goals are, like we said, avoid condensation in winter, maybe 70–80% RH max, but also don't let it get too dry. Below about 40% RH just becomes a serious problem.
Right, creates dust.
And this is key. You always need some minimum ventilation for moisture removal, even when it's freezing outside and you're trying to save every bit of heat. Can't seal it up completely.
Okay, so that leads us into air quality control. You mentioned dust and contaminants. This is where it gets maybe a bit alarming.
It can be, yeah. This is where it directly impacts the health of the animals, obviously, but also the people working there day in, day out.
So particulates, dust, where's that coming from mainly?
Mostly feed, bedding, or litter material, dried manure, and just skin debris from the animals themselves. Animal activity really stirs it up.
And the levels can get pretty high.
The handbook gives some typical measured ranges. Swine buildings, maybe 1 to 15 milligrams per cubic meter. Dairy barns are usually lower, maybe around 0.5. But poultry facilities, they average 2 to 7 milligm3, but, and this is the kicker, it can spike dramatically up to maybe 18 to even 29 milligm3 during periods of high activity, like feeding time or when birds are moved.
Wow, that's a massive jump. And this dust isn't just annoying, right?
Not at all. It carries allergens, bacteria, viruses, fungal spores, causing respiratory problems for workers, things like bronchitis or asthma, and definitely impacting animal lung health. Plus, these tiny particles carry odor compounds long distances.
Okay, so dust is bad. What about gases?
Gases are the other big one. Ammonia, NH3, is probably the most common chronic issue. It comes from the decomposition of urea in manure.
Right, that sharp smell.
Exactly. Typical levels vary a lot depending on the animal, the manure system, temperature. Maybe 7 to 37 milligrams per cubic meter in some poultry houses, or maybe 4 up to 37 in swine facilities.
And that's just the general room air.
That's often the room air measurement. But here's a really striking real case example the handbook mentions, specifically from lab animal facilities. While the overall room air might test negligible for ammonia,
Okay.
the concentration inside the individual animal cages could reach much, much higher levels, sometimes up to 45 milligm3.
Inside the cage itself.
Yes, and there was a specific study cited, Weiss et al., from '91, that found really dramatic ammonia levels in rat cages. They measured up to 260 milligm3 with 4 male rats per cage and 50 milligm3 with 4 female rats, just 9 days after the cages were cleaned.
260. Compared to what target?
Well, the ideal target is often below 7 milligm3, maybe even lower for sensitive research. It just shows how critical that microenvironment within the cage is. Even if the room seems fine, you can't just measure the room air and assume everything's okay at the animal level.
That's a huge difference. Really highlights the importance of cage-level ventilation or frequent cleaning. What other gases are a concern?
Hydrogen sulfide, H2S, is another one, mainly from anaerobic decomposition in stored liquid manure pits. Usually during normal operation, the levels are pretty low, maybe 200 to 500 micrograms per cubic meter in a typical swine barn. Pretty insignificant day to day. But during manure agitation, when they stir the pit before pumping it out, oh boy, levels can become acutely dangerous very quickly. The handbook mentions measured levels reaching 280 to 460 milligrams per cubic meter, and potentially spiking even higher, maybe 1.4 to 11 grams per cubic meter in localized spots. Lethal levels. That's why there are strict safety protocols, often requiring evacuation during agitation.
Wow. Okay, that's serious hazard potential.
Right.
What about CO2? We exhale it. It's in the atmosphere.
Carbon dioxide is more an indicator of general ventilation adequacy, rather than being highly toxic at typical indoor levels like ammonia or H2S. But it's still important. There was a case study mentioned, Barber et al., 93, looking at pig buildings. They found, unsurprisingly, that CO2 levels were almost always higher when the outside temperature was below freezing.
Because they reduce ventilation to save heat.
Exactly. And the handbook points out a really key economic calculation here. It says there's a very high penalty in heating cost in cold climates. If you try to use ventilation just to keep CO2 concentrations below a certain threshold, say 9,000 milligm3, which is a common worker exposure guideline.
Trying to flush out that much CO2 with cold outside air would just cost a fortune in heating fuel.
Precisely. So there's a trade-off. You might accept higher CO2 levels in winter than you would otherwise to keep heating costs manageable, as long as other critical contaminants like ammonia are controlled. Though worker health guidelines, like one suggesting staying below about 2,717 ilg-M3 to minimize respiratory issues, are also a factor.
So, faced with all this dust and gas, how do engineers actually control these contaminants? What are the main strategies?
The handbook lays out three main approaches. First, and they stress this is the most important, reduce the production at the
How
source.
do you do that?
Things like frequent manure removal, ideally getting it out within 3 days before it decomposes too much. Keeping floors and surfaces dry. Sometimes covering manure storage pits with water to reduce gas release. Diet manipulation can even play a role.
Okay, source control first. What's next?
Second is air cleaning, using filters or scrubbers. But this is mostly practical and economical for removing particulates, the dust. Gas removal systems are generally too expensive for large animal facilities.
But dust filtering helps.
It can, but filters need maintenance and add resistance to fans. However, there's a fascinating specific calculation example for dust control that's much simpler. Just sprinkling a little bit of oil, like canola oil, on the floor, maybe 5 milliliters per square meter per day.
Just a thin layer of oil.
Yeah, a very small amount. That simple trick can reduce the airborne dust concentration by more than 80%.
80% from just oiling the floor.
Yeah.
That seems incredibly effective for something so low tech.
It really is. It helps weigh the dust particles down and keeps them from getting resuspended. So that's source control, air cleaning, and the third method.
Dilution, right? Just ventilate more.
Exactly. Dilution through ventilation. Bringing in fresh air pushes out the contaminated air. It's very effective for gases, less so for settling dust particles. But again, it comes with those trade-offs we talked about: heat loss in winter, energy costs for fans, and the potential for drafts.
Ah, yes, drafts. So air distribution and velocity are important too.
Absolutely critical. You want uniform conditions throughout the space, same temperature, same air quality, and you generally need to avoid drafts, especially on young or vulnerable animals. Usually that means keeping airspeed below about 0.25 meters per second at animal level in moderate or cold conditions.
But that changes when it's hot, right? You mentioned air movement helps cooling.
It does. In hot weather, that same air movement becomes beneficial. Increased air velocity directly over the animals helps them dissipate body heat through convection and evaporation. It significantly improves their heat tolerance.
Are they at an optimal speed?
The handbook cites studies giving some targets for hot weather. Swine seem to do best with airspeed less than 1 meter per second directly on them. Cattle, maybe around 1.5 meters. And poultry can tolerate and benefit from even higher speeds, up to maybe 3 meters.
Interesting how it varies by species. So for cooling, besides just moving air faster, what other methods are used?
Evaporative cooling is very common, especially in drier climates. You have fan and pad systems where fans pull air through wet pads, cooling it evaporatively, or fogging and misting systems that spray fine water droplets into the air. Direct wetting of the animals can also be used sometimes.
What about other methods?
Earth tubes are sometimes used running intake air through pipes buried in the ground to use the stable earth temperature for pre-cooling in summer or preheating in winter. Heat exchangers can recover heat from outgoing ventilation air.
And standard air conditioning, mechanical refrigeration.
Generally, it's just too expensive for large-scale production animals because the heat loads are enormous. The handbook mentions you might need over 2.5 kilowatts of cooling capacity per cow. That's a huge energy cost. Wow.
Yeah. But it is sometimes used for targeted zone cooling, especially for high-value animals like individual sows in farrowing crates, where you just cool a small area around their head or body.
And they give calculations for that, too.
Yeah, specific examples like maybe 10 to 20 liters per second of cooled air just for snout cooling for a pig, or 30 to 40 Ls per so for broader zone cooling. And for those earth tubes, a design example suggests 15 to 50 meters of 200 millimeter pipe could provide about 150 Ls of tempered air.
Okay. The handbook also touches on insulation and building types, right?
It does. Discusses different types: cold buildings, which are minimally enclosed; modified environment buildings relying more on insulation and natural ventilation; and supplementally heated buildings using full mechanical systems for tight control year-round. Insulation levels are obviously key for managing heat flow.
And the ventilation systems themselves, how are they set up?
Most common is negative pressure. Fans blow air out of the building, creating a slight vacuum inside. This pulls fresh air in through carefully designed inlets.
Ah, so the inlets are crucial for distribution. Absolutely. Their size, shape, and location determine where the fresh air goes and how it mixes with the room air without causing drafts. There are also positive pressure systems, fans blow air in, and neutral pressure systems, but negative is dominant for simplicity and cost.
And engineers actually calculate how the air flows through those inlets.
Yes, there's a method called the system characteristic technique. The handbook gives the formulas. For example, one shows how the airflow rate, Q, through a simple slot inlet depends on the slot width, W, and the pressure difference, P, across it, something like Q, is proportional to W times the square root of P. You use these calculations to match the fans to the inlets and the building's leakage.
So you know how much air you're actually getting through the planned openings.
Ideally, yes.
Oh.
But infiltration, unplanned air leakage through cracks and gaps can really mess things up. There was a case study mentioned, Zhang and Barber 95. They measured infiltration in a swine building.
What did they find?
They found about 0.6 liters per second of leakage per square meter of building surface area at a typical operating pressure difference of 20 pascals, which doesn't sound like much, but
But it adds up.
it added up to 1.4 air changes per hour just from leakage. That's uncontrolled air coming in from who knows where, bypassing the proper inlets and potentially disrupting the planned air distribution pattern. It really highlights why building air tightness is so important for controlled ventilation to work properly.
That makes sense. Control the leaks so your controlled inlets do the work.
Exactly. And finally, the handbook covers fan selection, getting the right type and size, and different ways to control the ventilation rate as conditions change. Simple on-off timers, staging multiple fans, using multi-speed fans, or variable speed drives linked to sensors for temperature, humidity, or even gas levels.
Okay, that's a pretty comprehensive look at the animal side. Shall we shift gears to plants, greenhouses, and growth chambers?
Let's do it. A whole different set of challenges, but the same core principles of environmental control apply.
So, greenhouses and plant growth chambers, the basic goal is to overcome adverse outdoor conditions, right? To allow economical crop production or controlled research when it would otherwise be impossible.
Precisely. You're creating a tailored environment. The basic needs are similar to animals in some ways. Temperature, air quality, but light becomes incredibly dominant. Plus, you need the right gas mix, especially CO2, protection from pests, and a suitable growing medium.
For greenhouses, site selection matters, I imagine. Sun exposure.
Hugely important. Orientation to the sun is critical for maximizing light, especially in winter. The handbook even shows diagrams illustrating how roof slope affects light transmission at different times of year. Soil type, drainage, windbreaks, they all factor in. Even the shape of the structure and the type of glazing material affect light and heat.
Like how some big commercial ones are aligned north-south.
Right, those gutter-connected ranges are often oriented north-south to minimize the shadows cast by the gutters and structure during winter when the sun angle is low.
Heating these structures must be a major cost. How do they calculate the load?
Very similar to animal buildings, actually. You calculate the total heat loss, QT, as the sum of conduction loss, QC, through the glazing and structure, and infiltration loss, Q, due to air leakage.
Using those U factors again.
Exactly. You use the U factor, the inverse of R value, for the glazing and other surfaces, multiply by the area and the temperature difference between inside and outside. For infiltration, you estimate air changes per hour based on greenhouse type and wind, multiply by the volume and temperature difference. The handbook provides tables for typical U factors and air change rates.
And the heating systems.
Lots of options. Hot water or steam pipes running along the perimeter or under benches are common. Forced air unit heaters. Increasingly popular is underfloor heating, embedding pipes right in the concrete floor.
Is it very effective?
It can be. There's a specific calculation example showing a typical underfloor system can provide maybe 50 to 65 watts per square meter of floor area. That provides very uniform base heating.
What about fuel-burning heaters inside the greenhouse? Any special considerations?
Yes, absolutely crucial. Proper venting. Unvented combustion releases not just CO2 and water vapor, but also ethylene and other pollutants that can be very harmful to plants, even at low concentrations. You also need adequate combustion air supply.
Is there a rule of thumb for the air supply opening?
There is. The handbook gives a specific calculation. You need a minimum free area opening of 2,200 square millimeters per kilowatt of heater input, or ensure each opening is at least 0.65 square meters, whichever is larger. Very important safety and operational point.
Got it. Okay, cooling greenhouses. Natural ventilation first.
Often, yes. Using wind pressure differences and thermal buoyancy, the chimney effect, warm air rises and exits through high vents, like roof vents, pulling cooler air in through low vents, like sidewall vents.
But for more control, you need fans. Mechanical ventilation.
Right. Fans provide predictable airflow regardless of wind or temperature difference. The handbook shows graphically how the required airflow rate directly impacts the temperature rise inside the greenhouse compared to outside. More airflow means less temperature rise. Simple as that.
And evaporative cooling, like the fan and pad systems.
Very common, especially in hot, dry areas. Extremely effective. The handbook provides a quite detailed method to calculate the required airflow for these systems. You start with a base rate.
Like the 40 Ls per square meter you mentioned.
Yes, something like 40 liters per second per square meter of floor area is a typical starting point. But then you modify that base rate using several factors.
Factors for what?
Things like your site elevation, air is less dense higher up, the maximum light intensity you expect, and the maximum acceptable temperature rise you can tolerate inside compared to outside. There are tables for these factors, FE, FL, FTT. You multiply them together to get a combined adjustment factor, FH, for the base airflow rate. It's quite specific.
Okay, a calculated approach. What about winter ventilation? Do you still need it?
You do, surprisingly. Even when you're trying to conserve heat, you often need some minimum ventilation, maybe 10 to 15 Ls per square meter. Why?
Let me guess. CO2.
Exactly. Plants use up CO2 during photosynthesis. In a tightly sealed greenhouse on a bright day with low ventilation, the CO2 level can actually drop below the normal outside ambient level, which significantly slows down plant growth.
So you ventilate just enough to replenish CO2, or you add CO2.
Both are done. CO2 enrichment, adding pure CO2 from tanks or burners, is common when ventilation rates are low to boost growth.
Now, here's something really fascinating I saw mentioned about CO2 uptake.
Oh.
Something about airspeed near the leaf.
Ah, yes, that's a great point. Research found that just having a gentle air movement, maybe 0.5 meters per second, right at the surface of the plant leaf.
Just locally.
Yes, just in that microboundary layer. That air movement can be metabolically equivalent to providing a 50% enrichment of CO2 in the bulk air without that air movement. It helps overcome the diffusion barrier right at the leaf surface, allowing the plant to grab CO2 more easily. It shows it's not just about the overall CO2 level, but also how efficiently it gets to the photosynthetic machinery.
That's incredible.
Yeah.
Micro-level air movement makes that much difference.
Yeah.
Okay, let's talk light. Often the biggest limitation in winter, right?
Absolutely. That's where artificial lighting comes in, usually high-intensity discharge, HID lamps like high-pressure sodium or metal halide, to supplement low natural light.
And how do they measure light? For plants, it's not lux, like for human vision?
Correct. For plants, what matters is the energy available for photosynthesis. So the handbook emphasizes using measures like radiant flux density, measured in watts per square meter, WM2, which represents energy,
Okay.
or photon flux density, measured in micromoles of photons per second per square meter, which represents the number of photosynthetically active photons. Lux is weighted for human eye sensitivity and isn't a good measure for plant growth. The handbook provides conversion factors if you need them.
And they give actual recommendations for light levels.
Yes, practical tables showing target irradiance levels in WM2, how many hours per day to run the lights, and even the best time of day for supplemental lighting for specific crops. Like, you might need XWM2 for 16 hours for tomatoes, but YWM2 for 12 hours for chrysanthemums. It's very tailored.
Like a light prescription.
Yeah.
What about using lights to control flowering? Photoperiod control.
Right, using light to manipulate the perceived day length. This often uses much lower light levels, maybe just 6 to 12 WM2. The goal isn't photosynthesis, but signaling.
And incandescent lamps work well for this.
They do, even though they're inefficient for growth lighting. Their spectrum, particularly the far red light they emit, is very effective for triggering photoperiod responses in many plants, even at low intensity. The handbook gives calculation examples for spacing these, like maybe 150 W lamps every 3-4 meters if mounted 4 meters high, or 60 W lamps every 2 meters.
And they have tricks to save energy doing this, like interrupting the night.
Yes, often you don't need continuous light. Just interrupting the long dark period for a short time, say from 10 p.m. to 2 a.m., can be enough to create a long day effect. And to cut down on peak electrical demand charges, sometimes they cycle the lights during that interruption period, like having them on for only 12 seconds every minute. That uses only 20% of the power, but can still be effective biologically.
Clever. Energy conservation is obviously important overall. What are the main methods mentioned?
Things like thermal blankets or curtains drawn over the crop at night are huge, double glazing instead of single, insulating the perimeter foundation walls.
Thermal blankets seem common. How much do they save?
The handbook suggests they can reduce overall heat loss by 25 to 35%, pretty significant. But they also note potential downsides if the greenhouse becomes too tightly sealed, like higher humidity, potential for condensation drip, ethylene buildup if there are unvented heaters, or CO2 depletion becoming more likely. Always trade-offs.
Okay, let's transition to the really high-tech end. Controlled environment rooms, CERs, or phytotrons. These are for serious research or super high-value crops.
Exactly. These are basically tightly sealed indoor rooms or even smaller boxes, often with completely artificial light and very precise control over temperature, humidity, sometimes CO2.
Like walk-in coolers, but with massive lights inside.
That's a good analogy. And those lights generate a ton of heat, which the cooling system has to constantly fight against.
The electrical load must be enormous.
It really is. For planning, the handbook gives a calculation guideline. You might need up to 1,500 watts of electrical capacity per square meter of the actual controlled growing space, or maybe 1,000 W per square meter of the total building space housing the CERs.
Wow. And how much of that is just for cooling the lights?
For self-contained units, the cooling compressor's power draw is often around 80% of the lighting power draw. It gives you an idea of how much heat those lights are putting out that needs to be removed.
How do they reject that heat?
Depends on the scale. Small units might just vent heat into the surrounding room. Larger facilities use cooling towers or connect to a central building chilled water system.
Is standard chilled water okay?
Usually, yes, if the chambers are running at typical room temps, like 20-25 degrees C. Standard 7 degrees C chilled water works fine, but the handbook points out a potential real issue. If you try to run chambers very cold, say for vernalization studies, and use much colder chilled water, like maybe -10 degrees C,
That causes problems.
it can lead to high failure rates for the chamber's own refrigeration compressors. They aren't typically designed for such low suction temperatures, which can cause problems like poor oil return to the compressor, something engineers need to be aware of.
Good practical tip. Given the huge energy use, conservation must be a focus here too.
Absolutely. These things are energy hogs. One key strategy the handbook presents involves scheduling. Most experiments only need maybe a 12 to 16-hour daylight or photo period.
So you don't run them 247.
Right. And if you have multiple chambers in a facility, you can stagger their light-dark cycles. Instead of having all the lights, and thus the peak cooling load, come on at the same time, you spread it out. This balancing act can reduce the facility's peak electrical demand by as much as 25%.
Just by smart scheduling? That's significant. What about the lighting inside these CERs? Uniformity is key.
Paramount. For reproducible research, you need the light level to be as uniform as possible, both horizontally across the plant canopy and vertically down through it. The handbook refers back to tables showing specific examples how different lamps, like fluorescent tubes versus HID lamps, need different mounting heights and spacing patterns to hit a target irradiation level, maybe 18 or 24 WM/2 with good uniformity.
And lamps dim over time, right?
Right.
How do they manage that?
Yes, lumen depreciation is a real factor. Strategies include installing more lamps initially than strictly needed and switching some off, then turning them on later as the others dim, or just doing periodic bulk replacement of all the lamps on a schedule. Often there's a barrier, like glass or clear plastic, separating the lamps from the growing area to help manage heat and direct airflow properly.
Okay. Any other operational things to keep in mind for CERs?
Noise can be an issue with self-contained units. Filtering the incoming makeup air is critical to keep out pests, diseases, and pollen, especially for research. Ventilation rates are typically similar to greenhouses, maybe 10-15 Ls per square meter of growing area, mainly for humidity control and removing heat that leaks past the cooling coils.
Water management.
Crucial. Proper drainage for condensation is needed to prevent puddles, which can harbor algae, fungi, and pests like fungus gnats. Cleanliness is absolutely vital, often requiring separate rooms for potting, media preparation versus harvesting to prevent cross-contamination.
And keeping harvest areas under negative pressure.
Yes, especially important if dealing with pathogens or genetically modified organisms to prevent anything from escaping into cleaner areas or the outside environment. Sometimes autoclaves are required right near the harvest room for decontamination. The handbook also briefly mentions simpler warehouse-type facilities used just for holding plants, with varying light levels needed for survival versus active growth.
Wow. Okay, what an incredibly detailed deep dive. The sheer level of engineering thought that goes into optimizing these indoor spaces for, well, everything but us is really quite something.
It really is. It just highlights how deeply intertwined biology and engineering become when you try to create and maintain these highly controlled artificial ecosystems, All those calculations, the specific contaminant levels they worry about, the studies on air velocity, it's all aimed at hitting very specific, stable
And it's
conditions.
not just theoretical stuff, right? We,
Okay.
we saw real-world examples with big impacts, like that slatted floor cutting moisture load by 40%.
Exactly. Or the huge difference in ammonia inside a lab cage versus the room, or sprinkling oil to slash dust levels, or how just staggering light schedules in a phytotron can cut the energy bill by a quarter.
These aren't just abstract technical details. They have really direct consequences for animal welfare, plant growth, farm productivity, even the quality and reliability of scientific research.
Absolutely. It's engineering applied directly to the fundamentals of life support, tailored to specific organisms and goals.
So here's something maybe to mull over after digging into all this. As we humans spend more and more time indoors, and we focus more on optimizing our own indoor environments,
Yeah.
thinking about air purifiers, smart thermostats, circadian lighting,
Mm-hmm.
what could we potentially learn from the meticulous performance-driven engineering that goes into housing other living things for their peak health and productivity? Does thinking about things like air changes per hour, specific contaminant thresholds, or even radiant energy differently change how you think about the air you breathe or the light you see inside your own home or office?